goed. Ja, OBS gaat goed. Stop stream. Dan gaan we eens even checken of dat draait allemaal. YouTube. Dat is altijd goed. Channel. Beta. Oh. Oké. Dat is mooi. Ja, dat is allemaal goed. Oké, ik zit hier goed in de camera als ik hier zit te werken. En een boek dan, dat is allemaal, dat ziet er allemaal tip top uit. Ja, en dan kan ik al de chat daar neerzetten. Deze tuin en die zet ik maar geluid. Even zachtjes. Nou, dat moet zo. Nou, het geluid zit toch goed? Het geluid is hier beter? Nou, weet ik eigenlijk niet. Ja. Laat eens wat horen. Ja. Nou, ik weet eigenlijk niet horen. Beetje awkward. Oké. Goed zo doen. Time flies, ja. Het enige wat ik nog moet doen is straks de recording aan. Okay, students, welcome to the 10th lecture on multibody dynamics B. Still online, of course, due to the corona measures. The topic of today is rotation matrices and Euler angles. Rotation matrix is a large subject, and I expect not to be ready with that content, so next week we continue about rotation matrix, and therefore the homework assignment, the next homework assignment, number 10, will not be this week but will be next week. So for this week there will be no new homework assignments. Okay, that having said, again, rotation matrices and Euler angles, it's chapter 19 in the book. Yeah, let's start with Kahoot, right? When I look at the live stream, I see 89 people watching. Now, when I look outside, it's a nice, sunny, warm weather, so maybe that's one of the reasons that the turnout is a little bit lower. Okay, so, but let's do Kahoot. So, in-class quiz number 10. Let's start the thing. We do classical, right? Yeah, so everybody slowly is trickling in. That's not my student idea. Anyway. I have 93 watching and 92 players, 93 players, 94. Yeah, some of you team up, right, behind the computer. That's actually a very good idea to, as long as you're allowed to sit together in one room. Okay, so let's start the quiz. 5 questions again. First question is inkoppertje, as we say in Dutch. It's only 60 seconds, shouldn't be so hard. Just think about Euler and Newton. Yeah, indeed. So if everything is linear with the mass, so if the mass increases by a factor 2, then of course the resulting torque will also increase by a factor 2. Very good. Next question. This is about mass moments of inertia. Now, you have enough time for this. You have 2 minutes. So take your calculator, start calculating some stuff, and then you will find the correct answer. Just think about that mass moment of inertia is mass times distance squared, and that you can add everything up. It's like adding up mass. You can also add up mass moment of inertia, right? Yeah, very good. You could already discard two of the answers, because the smallest mass moment of inertia should of course be about the z-axis. If you look at the figure, then about this axis, I mean these are the shorter distances, so this should be the smallest one. So then this answer and this answer go away, and you have to decide between these two. This is actually too small, a distance squared. So without doing any calculation, you could already get the correct answer. Notice this is a multi-select, right? There can be more than one correct answer. So this is about the ordered equation of motion, given in the figure. And then the question is, if you take that about some point, what is a valid point? And again, notice it's a multi, there can be more than one correct answer. But it need not be. There's at least one correct answer. Yeah, indeed. The equation, Euler equation of motion for a rigid body in space is valid if you take as that point the center of mass, or if you take a fixed point when the body is fixed to the inertial world. Okie doke. Mass moment of inertia about the e-axis. So here we see a rigid body, three-dimensional, and it has within its local reference frame as a mass moment of inertia matrix, IC, and then there is some crooked axis. In this case it's given by 3/5, 0 and 4/5, and notice it's a unit vector. And then the question is, well, if you only rotate about this axis, what is the mass, what is the inertia, the mass moment of inertia that you feel? I mean, if it would be the x, the y, or the z-axis, that would be easy, but this is a combined axis. Think about the Euler equation of motion. Assume you have an angular acceleration in the direction of E. What is the torque you experience in the direction of E? Looking at the rate of the answers, this turns to be a difficult question. Yeah, as expected, right? Maybe you need more time, I don't know. So on average, more people are incorrect than correct, so I should talk about it. If this is the body, and if this is the mass moment of inertia, then and if this is the direction, and then assume, for instance, this is the direction of an acceleration, if you then multiply this with this vector, then you get a torque. But you get three components, right? So if you multiply that, you get 3/5 times 50, 0 times that, 0 times that, so that's 30. And if you multiply it with this one, you get minus 6, and here is minus 4, so you get minus 10. So the torque, well, was 60 minus 10. and then the last one is of course 80. But you don't need that torque in that direction, you need it in this direction, so you need to multiply that torque with those numbers, and then when you do that, you come up with the final answer being this 82. So, in conclusion, you would have to post and pre-multiply this inertia with this vector. Can be described by 3 finite successive rotations, so-called 3 Euler angles. And now the deeper question is, we have 3 Euler angles because in 3D again, this turns out to be a tricky question. Now, I could start discussing it now, but it turns out that the correct answer is part of the lecture of today, of course. That's always with the last question. And I can, I can disclose a little bit. Think about a lot of people, well, first of all, a lot of people think it has to do with 3 orthogonal base vectors, or 3 physical dimensions, or 3 angular velocity components. That's all not true. Because, bear with me, think of a planar case where you only have the xy plane, and then the rotation is only about the z-axis. So then you have 2 base vectors, so you would say, oh, then we have 2 rotations, and no, you only have 1 rotation in a 2-dimensional world. So the answer is a bit deeper, and I'm going to talk about that today. So hang on if you want to know the answer, correct answer. Why the 3 orthogonal planes is the correct answer. Okay, the podium. Who is on the podium? Shan, congratulations, very good. Good result. Flo, second, and first in line is... anonymous. I don't know. Well, anonymous, congratulations. Please give feedback. I'm going to save the results. Again, the direct download. And I'm going to save to the drive. It's always a good idea. Yep. Brut. Okay, what is the feedback? Is everybody happy? Oh. Okay. Yeah. This is done. This is done. I can leave that. I have saved it, and everything is up and running. Okay. So let's go to today's topic. And as I said, today's topic is of course rotation matrices and Euler angles. It's chapter 19 in the book, and it's a lot of material. Now I don't remember how many pages chapter 19 is, but in my mind, yeah, it is also a lot of pages, right? So that is 80, 30, so 25 pages. So yeah, that's a considerable part. So let's start by looking again at our result. The Euler equations of motion, I'm now focusing really on rotation, not so much on translation. So the Euler equations of motion in 3D, they are given by, well, the sum of the external torques, right? Well, that's not a nice torque thing. Torques. And then we do at the center of mass, or a fixed point, is mass moment of inertia times angular acceleration plus angular speed cross product with the product of the mass moment of inertia and the angular speed, which is the angular momentum, right? Now, if you look at this equation, then what do you see? You see inertia, you see angular acceleration, you see angular speed, but we see no angles. And that is interesting. So we see no angles. Although some of you could say, well, we have an angular speed, so that is a time derivative of an angle. Would be good if that is the case. Today we will see that it's a bit more tricky than that. Okay, so why do we need angles? Well, first of all, what is the whole problem? The problem is that we have some reference frame, and I start with, as a reference frame, an inertial frame. We have these nice curly letters, and I use N for that, for the inertial frame. Then the inertial frame, as I show here, is really fixed there to some big blob like Earth, so really inert. We have three base vectors, E1, E2, and E3. You could also say X, Y, Z, or whatever. For now I have 1, 2, 3. And then we have some potato, right? That is our rigid body. So this is our rigid body. And then in the rigid body we have that specific point, point C, right? Now let's put point C here, so that is the CM. Then attached to that body is some body fixed frame, and I'm just going to draw these, something like this. It's a body fixed frame, so I show again that's fixed to that body. There we also have base vectors. I call them with a prime, E1 prime, E2 prime, and this is E3 prime. We give it a name. We call it curly B, so that is the body fixed frame. And then within that frame we have a point P. Now, how do we find the point in space? Well, one way is to first travel to the center of mass by the vector RC, and then travel from that point to point P. And so this we call, how did I call it here? P with, that's not so smart actually. Let's do it formally. So this should be a vector, and that's P with respect to C, right? And then how do I find point P? Well, the final position, of course, of point P is this vector RP. Or in formulas, how do I find RP? RP is I go to the center of mass, and then from the center of mass I travel relatively with respect to C. Now this part, this first part, this is not the whole part, of course. Oh. Of course, this is what we call a translation, right? That is how this body is moved around. And this part has to do with rotation. Rotation. Now, why do I say that? Well, because, and now there's a deep thing, this vector within this reference system does not change. It is a rigid body, meaning that, suppose this is this rigid body and this is this point P, that within the rigid body, whatever the rigid body is doing, that point P always stays within that local reference frame. So my nose is always in front and in the middle of my second plane. Of course, if I were a flexible body, it would not be constant, but for a rigid body, and I'm pretty old, so I'm also very rigid, that doesn't change. So that is an interesting, with respect to C, so that is an interesting observation, and we will make use of that. For now, I will write a shorthand notation for this vector. I will just call it P, because otherwise I have to write so much. So I call this vector P. Okay, what can we do? Now, a vector is just a general concept. In the end, we have to calculate numbers. We need numbers. And if we have numbers, we have to say, oh, this vector, in which coordinate system is that expressed? So if we have a vector P, then we have algebraic components. And those algebraic components tell us how much do you have to travel along these different directions. So you say, oh, the P1 times E1 plus P2 times E2 plus P3 times E3. Now, these guys, these P1, P2, and P3, we call algebraic components of the vector P. Because you can express a vector in any coordinate system, right? And in this case, it's expressed in an inertial frame, in this inertial frame. So we have to distinguish that these components are the vector components in the inertial frame. For that we have a notation. So now again, and it may seem confusing, but now we write this curly n on the left top. We still we form these three components again in a vector, and we write it like this: P1, P2, P3. And these algebraic components, that is the thing which you use in MATLAB. So these are the numbers you use in MATLAB, because MATLAB has no idea of a coordinate system or whatsoever. It cannot do coordinate transformation, etc., etc. So this vector of algebraic components, the moment we see this curly letter there, we know, oh, it's a vector of algebraic components. Then here are these components given. Now I choose to express this P in this inertial frame, but for the same, in the same way, I can express this vector P in this coordinate system, in this frame. Sorry, coordinate system is where the origin, frame is only direction. So this vector I can express in this frame in the same manner as this. But so I can say this vector P, I mean point P doesn't change when you express it in another coordinate system. It's still point P. Now I'm going to use as base vectors these primes, 2 prime, and here 3 prime, and then then we have different algebraic components, of course. If I do, now I have, and I have to give them another name, so let's call them P1 prime, let's call them P2 prime, and P3 prime. Then again, if we say we want to put these in a vector, because finally we want to do calculations with them, so we put them in a vector, but now everything is expressed in the B frame, and if I write them down, it's these 3 numbers. Okay, now there's an important thing. These components, since B is body fixed frame, and body is rigid, these are constant. And that is a very important notation. Think about your nose in your head. Your nose stays your nose, irrespective of how you turn your head. And we will use that quantity. Okay. Now, what we actually want is we want to be able to express from one coordinate system to another coordinate system these components. That's what we call coordinate transformation, and we want to transform these to these, or these to these, or whatever. To do that, we go again back to our general expression, and we say, okay, if we have this vector p, how do we get the first component? So if we want to have p1, how do we get from the vector p, p1? E dot p is dot product of vectors, and you can also write it as E1 transpose times the vector p. That's the same, but I like the dot for now, and I'm not going to write very thick every time. Now, why does that work? Well, bear with me. So if I do E1 and I do the dot product with, and now I'm going to express this P1 in terms of P1 E1 plus P2 E2 plus P3 E3. Then of course I can pull out all these dot products, and I get P1 times this dot product plus P2 times this product, E1 with E2, plus P3 times this dot product, E1 dot E3. And of course, because we have orthogonal base, and I would really like to say we have more than orthogonal, we have orthonormal, because all the vectors are unit length. We have the following quantity, that if you have the dot product with itself, the answer is 1, and if you have the dot product with another one, it's 0. They are perpendicular. So with itself you get 1, with another one you get 0. And technically speaking, you can write that as E1 dot product EI with EJ equals 0. When is it 0? Well, I is not equal to j, and it's equal to 1 when I equals j. So that's the orthogonality. So with the help of the orthogonality, we can pull out our components. So this works. Again, we can do that same trick, but now we want to have the other component, right? We want to have in the prime. So P1 prime is, and again we take the vector P, and what do? Well, it's a sort of a giveaway thing, right? We multiply it with E1 prime. But now comes the super trick, and I didn't invent it, but you have to be super smart for that. So we want to find the transformation. Oh, that should be a. This is not a vector, right? Oops, it's a component. We want to know the transformation from these algebraic components with a prime to the other ones. So what do? Well, then in general you can write down again for the component pi is this ei, but now I'm going to take with the vector p, but for now I'm going to write the vector p not in terms of the e base, but the e prime base. So I say that's, what is it, p1 prime times e1 prime plus p2 prime times e2 prime plus p3 times e3 prime. It shouldn't be a dot, that's confusing. Okay, so then we have all these dot products now, and I write I here because I is then 1, 2, 3. So I actually should write 3 equations, but I'm a bit lazy, so I don't do that. And then again you can say, oh hey, but now I see what is going on. I pull out all the dot products, right? So I get ei dot product with e1 prime, and then and then I get ei dot product with e2 prime, and then ei dot product with e3 prime, and I have that 3 times, right? And then times a vector p1 prime, p2 prime, p3 prime. There should be a prime, not a 2. Should be a prime, yes. And I have that 3 times, or why don't we write that out for those I is 1, 2, 3. And then here we have 9 entries, and they actually are super simple. So this is E1 dot product with E1 prime, right? And we're working with the first. So again, and then we get E1 dot product with E2 prime, and we get E1 dot product with E3 prime. So 3 dot products. And the second one, E2, E1 prime, E2 dot E2 prime, E2 dot E3 prime, and the last one, E3, E1 prime, E3 dot product, E2 prime, and then E3, E3 prime. So 9 dot products, which is actually all you can do when you have a set of 3 vectors here and 3 vectors here, and you do dot products. What dot products can you form? Well, you can form 9 dot products, right? So now we have the transformation for given these components. How do we get these components? So there was a prime here, of course. So having the algebraic components in the body fixed, what are they in the inertial fixed frame? And this is actually then this transformation matrix. Now we can write it very shortly and compact with the indexes. So we said Pi, that component, is this vector EI dot product with EJ prime times PJ. And then I and J are 1, 2, 3, 1, 2, and 3, 1, 2, 3, 1, 2, 3. And of course you can also write it in this strange mixed thing. Rij is Pj. We have this index notation, Einstein index notation and summation. So we have to sum over the j, and then we have 3 equations. Now this guy we call the rotation matrix. Rotation matrix. So that is the topic for today, this guy. And apparently this guy is made up out of all these dot products. Or in other words, this rotation matrix Rij is defined as the dot product of EI with EJ prime. I, j is 1, 2, 3. If we now go back to our general description of matrices and vectors, right? So we have here, let's recap. We have our vector with our algebraic components. And then we said, well, in MATLAB, you use these algebraic components. And then we have this shorthand notation, because again, you can form these 3 components in a vector. But now they are tied to a base, to a frame, sorry, and that is the inertial frame here. And here the primes, they are tied to another frame, the body fixed frame. Now with that notation we can now apply here, because here we have these components and we can form a vector. So we can say, oh, the vector P, not so nice P, and it's a vector, and it's expressed in the inertial frame, is a rotation matrix, and we have this notation then for it, R times the vector P in the body fixed frame, and then we put the B here. And that is actually the way we write that. Then with this matrix R and B is then this rotation matrix, right? E I dot E J prime, where I and J is 1, 2, 3, and I have to tie that magically also to this guy. So that is the definition, and that is the way how we find our from a body fixed frame to a inertial frame, the algebraic components, and that's the stuff we use in MATLAB when we calculate things. Now sometimes you also want to go the other way around. So you say, well, I have these, I have this vector which is expressed in my inertial frame, and what are the components in my body fixed frame? So then it's like the inverse or something like that. Well, in our notation, we write that simply like, okay, I want the algebraic components, and then there's some rotation matrix, given the ones in the inertial frame. Well, then apparently I'm seeking for this rotation matrix. Now, looking at these expressions, you can say, oh, I find if I substitute this here, I find NP is N R of B times, now this guy goes there, R B N times P N. And of course the conclusion is that this product of these matrices, and I shouldn't write a dot because then you would think it's a dot product, but the product of these two matrices, and note how nicely the B and the B go down, is of course the identity matrix, is of course 1 0 0 0 1 0 0 0 1. Or in other words, if I have one of these matrices, then I can find the other one by just taking the inverse. Or in other words, the NRB is the inverse of the BRN. Curly N, and vice versa. Yeah, that will be a neat way actually to determine the inverse. There's even a more neater way, because why don't we use our whole definition here, but then we turn the whole thing around. So instead of starting from the PI's and going to the P primes, I start with the P primes and I go to the PI's. I can turn the whole thing around. So I can say, well, I can determine PI prime, and then by definition, that's EI prime dot product with EJ times PJ, right? It's just a definition. And then remember that the other one, PI was EI dot product with EJ prime P prime. That's just a kladje, so you remember that was in the other case. So this is the inverse relationship. And then if we look at this as the difference between this matrix, and if we associate this guy with R, Ij, then we see that here it looks a lot like this, only the I and the J are changed. So apparently, the inverse of Rij is equal to the transpose of this matrix. Or, when we use our notation here, if we have, for instance, the matrix which transforms from the body fixed to the inertial, and if we want to know the inverse, then that is just the NRB transposed, and that is exactly the inverse relationship, so P to N. And that is a very important relationship. You could also write it, if we use only as a symbol the matrix R, then the conclusion is R transpose times R equals I. And I always like to add when R is a rotation matrix, because it will not hold for any matrix, right? A rotation matrix is apparently some special thing, and actually this is the speciality which is in that rotation matrix. Now, how can we use that speciality? How can we characterize that? Well, first of all, how do we parameterize a rotation matrix? So if you look at the rotation matrix, then in general, a rotation matrix is a 3 by 3. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 entries, or 9 entries, or 9 numbers. And in general, you would say, oh, then I have to describe rotation, with 9 parameters, right? I mean, yeah, if you have 9 entries here, and I think they can be anything. Because we have these constraints or relations. We have these relations, and you can also read the relations as constraints. Constraints on R. And what are they? Well, it says R is a special matrix because R times R transpose is the identity. And you could read that as constraint equations. And how many constraint equations? Well, you have the identity matrix is 1 0 0 0 1 0 0 0 1. You have 9 constraints, right? Meaning that you have 9 parameters and 9 constraints. If you have 9 constraints and 9 parameters, there's only how many different rotation matrix can you have? Then there's only one rotation matrix. There's only one unique rotation matrix. With no free parameters. Well, that is a bit strange, right? You cannot imagine, because I mean we have a whole bunch of rotation matrices. Well, it turns out if you closely look at these relations, of course, R times R transpose, if I transpose that, that's equal to R times R transpose. Or in other words, all the entries which you have here, if you have an entry here, you have the identical here. And if you have an entry here, you have the identical here. So let's write the diagonals here like this. And if you have an entry here, don't use a 0, a plus. Then you have the same one here. So uniquely, we don't have 9 equations, but uniquely we have 1, 2, 3, 4, 5, 6. So we have 6 constraints. Because this is symmetric. So we have 6 constraints. So 6 constraints on 9 parameters gives us 9 and minus 6 is 9 minus 6 is 3, right? 3 free parameters. 9 free parameters. So the conclusion is, you can describe a rotation matrix in 3D with 3 free parameters. And of course that makes sense. Everybody would say, yeah, that's obvious. You have 3 axes, 1, 2, 3, and then you also have 3 rotations, right? Wrong. That's the completely wrong answer. Let's take a coffee break, and we continue at 2:45. I stopped the recording. Okay, coffee break.